Now I changed my mind about the test. I'm going to do it on Friday. I'm going to give it to you take home. I just hate to waste a lecture on the midterm, especially that we're taking our time and explaining everything in more details than I expected. So the review is turning out to be 2 lectures, actually, the transmission thing. So I'll have a test for you on Friday, and I'll give you a week to work on it. Okay? I'll give it to you. Now, I'll have very strict rules about the honor code on this side. Okay? I'll let you know on Friday. So we've been talking about the scattering parameters. And we mentioned that it is the preferred approach to analyzing electrical circuits at high frequencies. And in particular, when we're dealing with waveguides, where voltages and currents are not typically used, right? So if we have a 2-port device, we're thinking about an input of the form A with a reflection or an output coming from the first port is called B, and we give the subscript 1 to port 1. And on port 2, we have an, let's say, input on the lower side here, an input A2 and output B2. And we saw an example last time of a simple impedance in series, right? And we mentioned that whatever the shape of the network is, we can always come up with an S parameters where we can write the B vector in terms of the A vector, and we have the S matrix here. And we mentioned a few ways to get the S parameters. One of them is to write the impedance parameters and convert them, or the admittance and convert them. There is a conversion table in the book that you can resort to if you'd like. Or you can write your voltage and currents in the input in terms of voltage and currents in the output, and manipulate your equations until you get to the A and B. And we related the A's and B's to the voltages and currents. So we wrote the A as V plus I Z naught, or Z reference, if you wish to call it. The book uses ZR, which actually is a good notation, because it emphasizes the concept that this is just a reference impedance. It doesn't have to be a characteristic impedance of any particular element in the circuit. Divided by 2, square root of ZR. Right? And the same thing for the B. It just gets a minus sign here. Okay? So you can relate things to each other and get your expressions that way. If we are going to analyze using scattering parameters, that means we have to learn how to deal with signal flow graphs, because this is nothing but a signal flow graph. If you look at it from the inside, you are thinking of your signal A coming in, part of it reflecting back and contributing to the B1, and a part of it transmits, contributing to the B2. And if you add the A2 component, it will be part of it that transmits through to contribute to B1, and parts of it reflects to contribute to the B2. The coefficients are S21 here, S11 there, S22 here, and S12 there. So if we have a network, let's say here's a source connected to a transmission line, connected to a T network, connected to another transmission line, connected to a load. How would I analyze that using the scattering parameters? Basically, what you do is you break it into segments, and you represent each one by its own scattering parameters, and put the scattering parameters together. Right? So this one here is a two-port device. Let's call this device A. So this is S21A. This one here is S12A. This is S11A. This one here is S22A. The next device will have the same thing. I just drew it a bit bigger, that's all right. S21 device B, etc. Maintaining the arrows in the same directions as they should. And next will be this device here. And again, its own S21C, etc. And then finally the source and the load. All right? I'm keeping those until last. Let's take the example of how can we combine the S parameters of two devices for now, before I put the source and the load in the picture. How can I reduce those to one S parameters? So let's work on this board here. So here we have a situation where we have networks cascaded by each other. If you are cascading Z parameters, we know it's quite a bit of an effort to manipulate all these equations. That's why we invented the ABCD parameters. The ABCD parameters basically allow you to do the cascading easier. With the S parameters, there's also what's called the T matrix, or the T parameters, the transmission matrix, which can allow you to do that easily. But to go from the S to the T and back from the T to the S is laborsome. So typically, we don't do it unless we have to, right? Typically, we try to manage with without converting to the T matrix or the transmission matrix. All right? So these are the signal flow graphs of the two of them. I'm going to give labels in a second. S11A, I'm sorry, S21A, S21B, S11B, S11A, S22A, S22B, and this one here is S12A and S12B. And this will be like the A1, and this one here is our B1. There will be an A2 here, if you wish, I'm sorry, a B2A, and there will be an A2A. Let me write those in different color. This one here is B2A, and this one here is A2A. That's all for device A. For device B, that will be A1B, and
this one here will be B1B. Lowercase b. And finally, you have your B2 of the whole thing, which is actually, it's the same as B2B, if you wish, and will be A2 of the whole thing, which is the same as A2 of device B. So mathematically, you can write your equations. B1, B2 is equal to the, for device A, that's SA, A1, A2 is all for device A, and then B1, B2 of device B is equal to S sub B of A1, A2 for device B. And then add to them the equations, which is B2 of device A is the same as A1 for device B. And then A2 device A is the same as B1 for device B. And you combine them, do manipulation, and reduce them to B1A, B2B in terms of A1 of device A and A2 of device B. And what you get here is SAB, if you wish. That would be the combiner. So you manipulate those and try to put them in that form. Right? You can tell, it's going to take you a while to play all these games. Well, if we learn the rules of the signal flow graph, we can do it, like we say, by inspection, visually, right? We can just look at it and say, well, the answer is. How do we do that? We play some games. It's like when you do reduction of networks, you play games of opens and shorts and stuff like that. Here you play games of matching, right? So you say eventually this is the same as this one here, right? This one here is S21 of device C, which is AB actually, if you wish to call it AB. We never called it C, right? Just AB, okay. Because C is another device. It's good to maintain the names that way. And going up here, that's S22AB, that's S11AB, and this here is S12AB. And say this is equivalent to that, right? If they are equivalent to each other, they should be equivalent under any condition I apply or I impose. So if I take a different color chalk and say, let's connect a match here. So we connect a match here. I don't mean to draw a full solid line, otherwise you think it's a short circuit, right? If you put a match here, that means you are killing A2, right? You kill A2 coming from the final port, correct? Anyone disagrees? All right. We're all on the same page? Because it's going to get complicated a bit. If this is 0, that means there's nothing that will come through these two signals. These two lines here have disappeared from my diagram. Right? Nothing is coming back, so there's nothing fed here or fed there. Likewise, nothing fed here or fed there. So to simplify my network, I'm going to erase it. Right? I'm just going to pretend that I erased it. In this case here, the signal coming out here is actually, if I assume 1 here, this is already S21AB. So S21AB is a signal coming out of here, which is a signal coming out of there. Well, if I assume 1 here, that one will arrive here as S11A times 1, and then goes through this loop, and then goes through that. So actually this one here reduces to 1, S21A, and then there is a loop here, right? This one here doesn't matter because I'm looking at this signal here. Okay. And S21B. So what comes out here is actually S21AB. And we gave that rule last time. I wrote it down and I did not prove it. I said I will prove it next time, and I forgot to start the lecture with it. Okay, so I'm going to prove it to you in a few minutes after I finish this. So it's a product of these, S21A times S21B, divided by 1 minus the loop gain. The loop gain in this case is what? S11B times S22A. Done. Can you imagine the manipulation that you had to go through to get to that? With the signal flow graph rules, we can reduce it very nicely. With a simple game that we play. If they are identical, they have to be identical under output matching conditions. While I'm at it, I can look at the signal coming back here. The signal coming back here for the AB network is going to be S11AB. So I can write S11AB is equal to, that's the signal coming this way. This was the signal going that way. Signal coming this way here now, I have this, and I have that. Think of any other arrows that can bring back to the B1. These are the only two paths that will take you from A1 to B1. This one and that one, because this one is gone. That part of the network is gone. So when you have two parallel ways to get to your destination, that means you add them up. So that's S11A plus the other one would be the product of S21A times S11B times S12A divided by 1 minus the loop gain. So I have S21A times S11B times S12A divided by 1 minus the loop gain. S11B, S22A. I got 2 out of the 4. The other 2 are similar. You just do the whole thing from the opposite side. You do the similar thing from the opposite side, you can write also the same reduction. You can use the scheme to reduce any complicated network. You just have to be cautious and careful and make sure that you don't miss any path from one way to the destination. Right? Let me prove to you the loop gain thing on this board here before we go too far. Like we said, signal flow graph, if they are sequential, we multiply, right? If they join in, we add. If they branch, they are the same. If that's an x, you get x here and x there. Here xy, you get x plus y. Here SA or SX, SY, you get SX times SY. Okay? You are familiar with all those. So let's go through the loop gain. You have this SX, one coming in, and then you have a loop, call it SZ, and you have an SY here. And we're claiming what comes out here, these are multipliers. The white are multipliers and the yellow are the signals, okay? These are the signals. I have one here, so I get here SX times SY, 1 minus SC. Okay, let's prove that. To prove that, I'm going to make this space here, give myself some space in the graph. I need a little bit of space. I'm going to do this, do that. I'm going to make my loop like this. Right? So that's my one. And this is my SX. That's your multiplier. SY is multiplier here. SZ is a multiplier there. So you can see that this one here is branching, and this one here is mixing, right? So I have 1 times SX, the signal here now is going to be SX, right? 1 times SX. What will it be here? It will be added to that. I don't know what this is for now, okay? Because that depends on what comes out here. So I'm going to call this one here S lower alpha, all right? It's not any name, S alpha. So what I get here now is the sum of Sx plus S alpha. 1 times Sx, if you wish, plus S alpha. That signal is going to branch here and there. So right here is the same thing, and right here is the same thing. These are all the same exact values. Branching, you get the same answer, right? So what you get out here now is Sy times that. 1 times Sx, I'll just write it as Sx, okay? Plus S alpha. Meanwhile, this gets multiplied by Sz to give you S alpha. So S alpha here is actually Sz times this one here, which is Sx plus S alpha. Right? S alpha is that signal times Sc. So you can rewrite this one here as S alpha times 1 minus Sz is equal to Sz times Sx. For S alpha is Sx times Sz divided by 1 minus Sc. Okay? Now, I want to get the output here. So this output is equal to Sy times Sx plus Sy times S alpha, which is right there. Sz Sx divided by 1 minus Sc. We make a common denominator of 1 minus Sc. You get Sy Sx minus. Wait a minute. There's a parenthesis here. Sy comes out. Sx minus Sx Sz. What did I do wrong? I need to take the Sy out. Yeah, that's what I did wrong. Okay? Plus Sx Sc. That cancels that. You end up with Sy Sx divided by 1 minus Sg, which is this. You must have seen this before when you discussed oscillators, right? Because what we do on oscillators, how do you make an amplifier oscillate? Right? Make a positive feedback. If you do a negative feedback, you drop the gain. If this, your feedback element, is negative, then the denominator is greater than 1, and the amplifier gain now is dropped by that coefficient. If you make that negative feedback, that's a feedback. You're feeding from the output back to the input. Right? So that becomes greater than 1, that means you drop your gain. That's basically the built-in feature in human being when you see a danger, all right? What happens? The signal is fed back to your brain to tell you what? Drop your advancement, right? Stop. Okay, that's a negative feedback. If we lose that negative feedback and get some positive feedback in your brain, what's going to happen? You throw yourself from the balcony, right? Or in fire or what have you. If you have positive feedback now, and suppose you make the positive feedback, make that loop gain is equal to exactly 1. What do you get now? 0 in the denominator, and that makes your gain go to infinity. And that's a condition for oscillation. Because how do you get an output without an input? You need an infinite gain. Okay? So what we do is basically take some of the signal from the output, feed it back to the input, and adjust the loop gain to be exactly 1 at the frequency of interest and the amplitude of interest. Right? If it is a linear system, that means it's always infinity. That oscillator is going to grow any noise. There's no signal in, maybe a little noise that will go in, get an infinite gain, comes out to be infinite output. The signal goes to infinity, the voltage goes very high, the current goes very high, the device burns out. Right? That's why we always rely on the nonlinearity of the circuit, or we put some nonlinearity on purpose to make sure that we control the amplitude from growing all the way to infinity. Right? So we adjust the loop gain at the amplitude of interest and at the frequency of interest to be exactly 1. We get the oscillations at that amplitude and at that frequency. If you let go, you get something goes wrong. Okay, so that was the equation that we used in dealing with these loops, right? Now we need to add the model of these devices. These are the terminal devices. In between, we learn how to do it. We can reduce these two first, and then we can put SAB here, reduce it with SC, we have an SABC. The whole thing is now reduced into a two-port network. That's typically what we draw. And we have a load here, all right? The load is simply a one arrow, okay? Because if you have a signal here coming in, it will reflect there. Okay? Like here, look at this. The signal here will reflect there. So you have an S11 of the load. S11 of the load, since it's only one device, we call it gamma L, right? We don't need to call it S11 of the load. Gamma of the load, the reflection coefficient of the load, is our S11. We come to the source side, and that's a bit tricky. So I'm just going to do it on the side first here. Here's my source. I want to represent that by an S parameter thing here, right? Here's my S parameters. There will be a B coming out and A coming in. Obviously, to derive the model here again, we are going to play the same kind of game. We say if we have no source, there will be a reflection. So in the absence of the source, there will be a reflection coefficient here, gamma S, right? ZS. But the source puts in some signal in, so the presence of the source is going to put that signal in here. So that's a typical model for the source. S parameters, model of a source. The expression for that is really of not that much importance to us, because after all, most of our analysis is related to the impedance levels and S parameters rather than the voltage level and the power. All right? So I'm not going to give you the expression for that now. I'm just going to say it's an X, whatever it is. It's going to ratio out in our analysis. How much is X in terms of VS and ZS? The equation is likely in the book. I haven't checked it out. So what you do now is put your source in. I'm going to put that here as gamma S and X of the source. And this is going to be your S21 of the device here, which could be a reduction of many. S11, S12, and S22. So if I have a monitor sitting over here, and a monitor sitting over there, which is typical. Usually you'd like to see the reflection, overall reflection, and overall transmission. So monitor at the source and monitor at the load. We should call the monitor 1 and monitor 2. What will monitor 1 see? How much is the signal here? How much is that signal there? Right? So we're going to call this one here A1, we call that a B1, which is really the typical notation. And we'll call this a B2, we'll call this an A2. How much is A1 in terms of XS? How much is B1 in terms of XS and likewise? What we do is reduce the network. The way we typically do is impedances and, like if you have a situation where a network is like this, you stop here and you reduce that to one impedance, and then you work out the two parallel impedances, and then you combine them in series with that until you eventually get what we call a Thevenin's equivalent, right? We can do the same thing. Basically, our objective here is to find gamma input. So instead of saying A1 and B1, I want to find gamma input in this case, which is B1 over A1, gamma input. So we start the reduction from the output side. We have, I'm going to reduce the clutter in the drawing here, because when we do this, we'll do the same thing from the output side. That's all. Just start from the other side. So you want to reduce that combination. So we resort to the signal flow graph rules. I have this going into that, coming back here with that. So the gamma at this location is basically the loop gain, the transmission gain over 1 minus the loop gain. The transmission gain is gamma L, 1 minus loop